Welcome back. So, on the last video, we we were talking about we were discussing the topic 2.5, which is about homogeneous transformation matrices. Transformation matrices, and this topic is like an introduction to the topic 2.6, which is the topic that we will discuss on this video, which is representation of transformations. So let me write this, representation of transformations. And on the topic 2.5, we saw why it's important to maintain a matrix on the quadratic form, and we discussed the reasons why it's interesting for us, and they were because it's easier to calculate the inverse of a quadratic matrix than the rectangular matrices. And the second reason, it was because to multiply two matrices, uh, their dimensions need to be equal. So the topic 2.5 was very short, very it is like a briefly introduction to the topic 2.6. So let's discuss this topic. Okay, so a transformation is defined as the realization of a movement on a space. So let me write this. Realization of a movement on the space. When a referential, and it can be a, a vector or a object, an object, or even a movable referential, are moving on a space in relation to a fixed reference system, and we can draw what we are saying, what I'm saying. A referential in a reference system, that can be a body, um, which is object, or a vector. And let me draw the vector, a vector t. And now we can represent this vector t based on this reference system. So this is our universe reference system. And when this is our moving on the space, we represent this movement similar to the representation of a referential. This is occur because a transformation is a change on the state of the referential, and that means a change on the localization and position. Remember, this vector can be moving around on this reference system. With that being said, the transformation can be one of those three forms. First, we can have a transformation that we call of a pure translation. We can have a transformation that is a pure rotation, and on the last we can have a transformation that can be both a translation and rotation. So we can have those three transformations. Okay. Now, the topic 2.6 ends here and it starts the topic 2.6.1, which is an introduction on how, sorry, an introduction on the way that these transformations work. So we're going to see first how it works a pure translation. So the topic 2.6.1 is the representation of a pure translation. Let me skip the text. Let me skip the text and write the transformation in the form of a matrix. And I'm gonna explain this matrix for you. And after that, I'm gonna read the text. And also we can solve a example. We're gonna solve the example 2.6. Okay, so um, let me finish this. The x, the y, the z, one. As I said on the last video, we add this fourth row, which is the scale factor W, and this scale factor, it has influence on all these elements. So anytime that you see um, this matrix, this matrix, that matrix uh, tell to us it means a pure translation. Why? We need to draw the axis system. So that are reference system, um, also a axis system, and we have our we have the unit vectors, x, y, z, x, y, z, x, y, z. Um, those are unit vectors. So realize on the axis x, as it pointing to this direction and only on this direction, this unit vector is only point on the direction of the axis, on the axis x direction. So the other values for this unit vector are 0. Um, these are let me if I change this, sorry, if I change this for the other reference system like O, and it is a unit vector, and S are only pointing on this direction, we only will have this value 1 and the other values will be 0, because um, let's suppose we are decomposing this vector on the other components of this reference system. So this way we can have a values different of 0, but as this unit vector is only pointing on this direction, so as the own name are saying, is a unit vector and the other values is 0. Okay, and as I said, this other column is added, is the scale factor, and this fourth column are the three components of the period translation, which is the vector d. Now imagine that you have this vector d, and now this vector is decomposed on the other components of this reference system. Okay. So what I wanted to understand here is that these columns, it represent the movement of a vector or a object that can be a rigid body or even a referential. Okay, now I'm gonna read the text that I skipped. If a referential um, if are moving on a space without any orientation, change on the orientation, um, that means this referential Um, and this vector d represented by on this matrix by dx dy and dz is a referential, just like if we plug right here a rigid body, this is going to be a referential. And if this referential, it doesn't have any change on the orientation or orientation, that means that this referential are doing a pure translation. And this matrix T is, is telling this to us as I explained to you. Uh, okay, because the unit vectors, it means on the same direction. Now let me draw a representation of a pure translation. Let's use this that I already have drawn. So we can have a vector in this vector, and now let's say that this vector is a robot arm. And better, let's look right here a rigid body, and we have our reference system, and this rigid body uh, that can be linked on a robot arm are going to do a translation, pure translation movement. And on the end of this, we have other reference system because it's already referenced. So if we tracking right here, we are tracking right here as is referenced to this reference system. We're going to be able to track on the end of the transformation. So you're going to change to is a vector P, a reference to reference P, and the D is the transformation of pure translation. So now start the coolest part. Um, let's say no. Let me copy this, and I'm going to explain based on this. Now you saw that uh, why is useful a reference system to be able to track any part of the rigid body which is referential, or a vector that can represent a robot arm. So let's say we wanted to know the the position and the orientation of a rigid body or a vector on the end of the transformation. As we are talking about a pure transformation, let's say we wanted to know the new position and orientation. So the new one is going to be the the first, which is this vector, which is the values of the initial position in orientation, and that is the matrix they are representing a pure translation. So we don't have any movement uh, of rotation, and that's why we are completing with zeros. The x, the z, one. And now we multiply the old one, this, by the new one, and we're going to have the final orientation and position of the rigid body or a vector. Now I realize that I changed the order um, of my explanation. Uh, that is the matrix of the vector P, and that is the matrix of the vector D, which is this one. And multiplying both of these, this is the referential. That can be a rigid body, or even a referential system, ref system, as you are seeing. And that is the reference system. And multiplying both of these matrices, we're going to have our new one, which is the final orientation position. Plus dz plus, okay. And we can write this equation or new matrix that represent the final orientation and position is the transformation, and we write this transformation dx, dy, dz times the old position of a rigid body or a vector, which is a referential. Okay, now we are ready to solve the example 2.6. It says that a referential f was, which is this one. Let me, this one, this referential. It was moved 10 units right here alongside the axis y and 5 units alongside the axis z of the reference system. And it asked for us to find the new location of the referential. So we just need to use this equation, and we're going to find the final orientation of the final localization of the referential. So I'm gonna be briefly on this. So the final orientation is the translation times the initial localization of the referential, and doing this we're going to obtain the following. Okay, the new one is equal to the transformation of translation. At this point, you know that when a rigid body, a vector, which are referentials, they don't make any rotation movement. If they only do a translation, the matrix that represents this referential is going to look like this. Now we multiply this movement of translation by the position, the initial position of the referential. And after do this operation, we are able to find the final localization of our reference system, of our referential. Sorry. This matrix represent the localization of the referential. And I'm referring to this. That is the final position of the referential. The referential was first at this localization, and after the translation, the pure translation movement characterized by this this matrix, after this transformation, which is a transformation of pure translation, we we end on this localization, and is represented by this matrix. Okay, that's it. Now you know how to calculate the final position, the final localization of a referential, which is multiplying the initial position by the, the movement of translation or rotation. But now we are about rotation movement. We will talk further. And for now, is all. Thank you. See you on the next video where we will talking about the representation of a pure rotation. Bye bye.